Okay, so we are in section 5.6 to 5.9. We're now going to be looking at thin-walled tubes, and we developed a couple of equations in class. If we have thin-walled tubes, then I know that the shear stress that I'm looking at is equal to T divided by 2 thickness area mean. And we'll talk about that area mean in just a second. I also know that when I'm looking at the angle of rotation, it is TL over, I think, 4, yep, 4 area of mean squared G. And then we have this funky little integration thing with ds over thickness. Okay, and really all this is if we had some cross section that we had functions, um, we might have to do integration or whatever, but this is literally ds is the length of the perimeter of our area and then thickness. So we look at center lines. We look at the center line of a section, and so that length is just going to be the length of that center line. And we'll talk about that here. So for a given maximum average shear stress, determine the factor by which the torque carrying capacity is increased if the half circular section is reversed from the dashed line position to the to out. So this would be the same amount of material. It's just that I would have either my circle coming in or flop it out, and let's see how much increase in capacity that we get. When we are looking at cross sections, we have to remember that our area mean is the center line area. So if we had a box like this, we are going to have a center line that is the average, I guess, if you want to call it the thicknesses. So that mean average is what is inside that center line. The length is going to be the length of that center line that's creating that internal area. So as I'm looking at this, okay, my tube is, my thickness is 0.1 inches. So if this is 120 inches to the top, and I mean 1.2 inches to the top and the bottom, if I need that internal, let's see if I can get a red pen in here and see what that looks like. If I need the internal, then I am going to have to figure out, well, what is my center line value? What is this actual center line? Here's my center line. Okay, center line, because that's the part that really matters, center line. So if it's 1.2 to the top, I mean 1.2 from bottom to top, coming back down the center line, I'm going to be coming back down, a thickness divided by 2, okay, so halfway, and I'm going to be going up a thickness also divided by 2, going up, which is basically entire thickness. So when I look at this dimension, it's going to be 1.1 inches, okay? When I'm looking in this direction, okay, I'm going right to this point. That's exactly where I'm going. But again, I'm having to come in part of a thickness, okay? I'm having to come in part of a thickness. So instead of a 1.8 inches, I'm actually looking at 1.75 inches. And that's how we're getting our internal lines. So we've got this, and then if the circle is on the inside, coming around, if I know that it's a 0.6 to the outer, 0.5 to the inner, then I know the radius to my center line is going to be 0.55 inches, okay? So if I'm looking at the area, then I could make this a box. See my box? And then I could subtract out the area of the inner circle. Likewise, I could make a box and I could come back and add in that same amount of area of the half circle, but this time it's going to be a positive area versus a negative area. So either way, I have a box like so, 1.75, 1.1, okay? area in minus that area that comes out from the circle. And here, my radius is 0.55 inches. If I pop that half circle out, I'm still going to have that square of 1.75, 1.1, but this time I'm going to be adding that additional area, radius of 0.55 inches. Okay. Now, when I am looking at the actual path then for DS, 1.75, okay, we're going to have, what is our actual path? Let's look at a different color maybe. I don't know. Let's try this one. When we're looking at our actual path, we can see we're going to be going 1.75, 1.1, 1.75, and that will be our total path when we are looking at this. Here we have 1.75, 1.1, 1.75. Okay, so it's the same amount of path. It's going to be 2 times 1.75, 1.1, and then the path of half the circumference of a circle. Okay, so let's start back with this. Given the maximum shear stress, the average shear stress of T over 2TAM, determine the factor by which the torque carrying capacity, so torque equals shear stress 2TAM, if we reverse that out. So we can now find the torque of one shape divided by the torque of the other shape, or vice versa, to see how we're increasing our properties by reversing that. So let's look over here. We have thickness is the same for both. That's going to be 0.1 inches. Here, my area mean is 1.75 times 1.1. Okay. 1.75 times 1.1, and here we're going to be subtracting. Okay, the area of a circle is pi r squared, but we only have half that circle. So our area mean for inverted is 1.75 times 1.1 minus pi 0.55 squared divided by 2. The area for this bottom segment where we have not inverted, it's still going to be 1.75 times 1.1. We still have this entire area, but this time plus pi r squared divided by 2. Okay, so that would be our area mean. Our thicknesses are the same, the T is the same, the shear stress is the same. So when we're looking at this factor of torque divided by torque, we are going to go with, we want to find that it's increased. So we're going to have the top, this is going to be our inverted on the bottom. And this is going to be, I guess, not inverted. So going out. Okay, equals shear stress 2TAM, shear stress 2TAM. So the factor really then becomes how we have changed that area. So 1.75 times 1.1 plus pi 0.55 squared over 2 divided by 1.75, 1.1 minus pi 0.55 squared divided by 2. So let's look at this factor. 1.75 enter, 1.1 times pi as a number, 0.55 times 0.55 times 2 divided by plus 1.75 enter, 1.1 times pi as a number, 0.55 times 0.55 times 2 divided by, this time we're subtracting, minus. So my factor is 2.4 divided by 1.45 and 1.66. So I've increased, Okay, I've increased the capacity um, just by popping out that circle instead of reducing because it's the same amount of material, right? It's the same amount of perimeter if we were looking at rotation, but what does change is how we have this area, because here we are reducing the area again, so it's going to look like this, and here we are increasing that area, so it's all of this plus that.